So in this second lecture, we're gonna review three topics: quadratic inequalities, systems of inequalities, and sign of fractions of polynomials. So the first object is something in the form x squared minus 9 greater than 0. Second object is something in the form x squared plus x plus 1 less than 0, and x squared minus 4 less than 0. And the third object is something in the form x divided times x cubed minus 1 greater than 0. So these are all inequalities that we might find in when we study functions, because, for example, we have a function that describes the velocity of the seismic waves in the Earth, and we want to know when this function is positive, for example. So let's look at quadratic inequalities first. And this lecture is going to be just a set of examples so you can get familiar with the topic and the methods for the solutions. So the examples are always in black. So here, let's start with something simple. Minus x squared plus 4 less than 0. So the first thing that we do is to study, well, the first thing that we do in this case could be to change the sign if you feel more comfortable working with a coefficient which is positive. Now, if we change the sign, we also have to change the sign of the inequality. Now, the first thing that we do is we study the associated equation. Or the associated equality. So we want to know the values of x such that x squared minus 4 is equal to 0. Now, this is pretty simple because this can be written as x minus 2 times x plus 2 equal to 0. So we have two solutions, x1 equal 2 and x2 equal minus 2. So this is pretty straightforward. Now, we haven't solved the inequality yet. We just solved the corresponding equality. So now, this one here is a parabola, and we know that the intersection with the x-axis are in minus 2 and in 2. Well, in this case, we also know that it's going to intersect the y-axis in minus 4. So this is a parabola that looks like this. Now, we want to know the values of, or the intervals of values of x such that this object is greater than 0, which means above the x-axis. So it's going to be in this area of the plane and this area of the plane. So it's x greater than 2 or x less than minus 2. So we can write the solution as a set of values of x in the set of real numbers such that x is less than minus 2 or x is greater than 2. Okay, let's try another example. X squared plus x plus 1 greater than 0. Now we studied the associated equation, x squared plus x plus 1 equals 0. We can compute a solution, x12 is equal minus 1 plus or minus 1 minus 4 divided by 2. Now the delta in this case, so the part b squared minus 4ac is equal to minus 3, so it's negative. So it means that there are no intersections. So this parabola is either all above the x-axis or it's all below. Well, if you just plug in a number, you're going to find out that this is always above the x-axis, because in 0 you get 1, in 1 you get 3. So this is well, I didn't do it right. Let's plug in some numbers just to, in 1 it's going to be 1 plus 1 plus 1 is 3. In 0 it's 1. In minus 1 it's going to be 1 plus 1 2 minus 1 is 1. So it's something like this. Okay, so when is the this equation greater than 0? Well, always, right? So this expression is always positive. So S is just all x's belong to the set of real numbers. Well, what if we try to do x squared plus x plus 1 less than 0? Well, it is exactly as before, right? So the delta is still negative, so it's the same, something like this. Now, we're interested in the values that make this expression negative. Well, this expression is never negative, so the set of solution is the empty set. There are no solutions for this inequality here. Okay. Well, let's do one more time. X squared, or well, let's maybe a couple. 2x minus 8 less than or equal to 0. Now, remember that we read this sign greater than or equal to 0. And this sign less than or equal to. So the expression 4 greater than or equal to 3 is true. It happens that sometimes that students say this is not true because 4 cannot be equal to 3. This expression means that one of the two conditions must be verified in order for the expression to be true. So either 4 is greater to 3 or 4 is equal to 3. Now 4 is greater than 3, so this is correct. I know it seems trivial, but sometimes students forget how to read logical operators. So anyway, we do the associated equation. This is going to be x12 equal minus 2 plus or minus square root of 4 plus 32 divided by 2, which is equal to minus 2 plus or minus 6 divided by 2. So x1 is equal minus 4, x2 is equal 2. Well, another way to do it would have been to factorize this one here as x plus 4 times x minus 2. Because plus, so this 2x can be anyway. Now, again, we draw the parabola. We know that the intersections are in minus 4 and in 2. So it's going to look something like this, approximately. And we're interested in the solutions that make this expression less than or equal to 0. So we are, let me change the color. we are interested in the solutions that make this expression negative or equal to 0. So we're interested in this part of the plane. So the solution S is the set of x belonging to the set of real numbers such that minus 4 is less than or equal to x less than or equal to 2. Well, let me do one more case when there's only one possible solution in the associated equation. So again, if you don't like the negative sign, you can always write it as with a positive sign by changing the sign of the inequality. We study the associated equation. This one here is pretty easy because it can be written as minus 3 squared equals 0. So we get x equal to 3. So we have one identical solution. Now let's draw the parabola. Well, it simply means that the parabola is going to be tangent to the x-axis in 3. Now we want to study when this expression is less than or greater than 0. Well, it's never negative, and it's equal to 3 only in x equal 3. So the set of solutions is x equal 3. In this case, the solution of the inequality is unique. Well, again, one more time. What happens if it's not written in the explicit form? Well, then you might have to do some math first. So here we have 2x squared plus 4x greater than or equal to x squared minus x minus 6. So we move everything to the left. We get 2x squared minus x squared plus 4x plus x plus 6 greater than or equal to 0, x squared plus 5x plus 6 greater than or equal to 0. This is easy. This can be written as x squared plus 6x minus x plus 6. Well, actually, let's use the usual formula so we're consistent. x12 is equal to minus 5 plus or minus 25, 5 squared, minus 4 times 6, 24, divided by 2. So it's minus 5 plus or minus 1 divided by 2. So we get minus 3 and minus 2. So again, this one here is a parabola that intersects in minus 3 and in minus 2. Oops, sorry. Well, as you can clearly tell, art is not my favorite subject. Try to do it in scale, approximately. Then this is going to be a parabola that looks like this. It's going to intersect in 6, but we really don't care about this part. So when is this thing positive? Well, it's positive when it is below minus 3, and it's positive when it is above 2. So it's x less than or equal to minus 3, and x greater than 2. Well, if you want to be a little bit more precise, it's going to be x in the set of real numbers such that, minus 2. Okay, I think we had a good overview of inequalities. Now, what happens if we do a system of inequalities? Well, let's start working with simple examples. Well, we have x greater than 0 and x greater than 5. Well, this is pretty straightforward. I'm just going to put number 1 and number 2 so that I don't have to rewrite the equations every time. This is the inequalities every time. This is the first inequality. This is the second inequality. Now, let's use some graphical representation because otherwise it becomes a little bit messy. So here we have the set of real numbers. This is 0. And here we set another set of real numbers with 5. Now, x greater than 0 means that all the values above 0 are acceptable. Oops. And x greater than 5 means that all the values above 5 are acceptable. Now, in a system, both inequalities must be satisfied, so we only care about the regions of the plane, or of the set of real numbers, where both inequalities are satisfied. So in this case, the solution is x greater than 5. Because if x is greater than 0 but is not greater than 5, then only one equation is satisfied. So again, both conditions must be verified. That's the key to solve inequalities. So if we have x minus 2 greater than 0 and x minus 2 less than 1, well, we can solve them independently. So this is x greater than 2 and x less than 3. Now we can use that graphical representation that I showed you before. Here we have 2, and all the values greater than 2 are acceptable. And then here we have 3. All the values below 3 are acceptable. So now we have to look at the sections or the intervals where both equations are satisfied. So in my graphical representation, the solid line means true or satisfied. Well, that's right, true. And the dashed line or dotted line means false. So in the system of the equations, we look at all the intervals where both conditions are satisfied. So again, the solution here is going to be x, the set of real numbers, so such that 2 is less than x less than 3. One more example with systems of inequalities. So we have x squared minus 4 greater than 0 minus x plus 1 greater than 0. Okay, so this one here, well, we're not going to do anything with this one here right now, but we can change the sign of this one here if you feel more comfortable. So it's x minus 1 less than 0. Okay, let's solve this one here first. So equation number 1, this is inequality number 1 and inequality number 2. Well, number 2 is easy. I'm going to solve it right away. X minus less than 0 means x less than 1. So this was pretty simple. Now, equation number 2, well, we know that the two solutions, if we do x minus 4 equals 0, the two solutions are plus or minus 2. So this means that this is a parabola that intersects in plus 2 and minus 2. And we want to know when this is positive. So this is going to be positive here and here. So it is x greater than 2 or x less than minus 2. Now we have to combine this equation with this equation here. sorry, this inequality with this inequality here. So again, we're going to use our graphical representation. So this one here must be represented at the same time, because this is obviously x cannot be greater than 2 and less than minus 2 at the same time. So this is here, there's or. But then when we combine the two, this is going to be and. So both of them, they must be satisfied at the same time. So here we have minus 2, here we have plus 2, and then we're going to show the solution of the first equation, the inequality. So it's x less than minus 2, x greater than plus 2, and then in between it's not verified because it's negative. So it's not, it doesn't satisfy this condition here. Now the second one is easy. 1 is going to be approximately here. And then all the values below 1 are going to be accepted. All the values above are not going to be accepted. Now we only care about the intervals where both solutions are verified, so it's going to be here. X belonging to R such that x is less than minus 2. Well, you can try if you want. For example, let's say that I plug in 0, right? Well, if I plug in 0, the first one is minus 4 greater than 0, which is not true. The second one is verified because it's 1 greater than 0. So this, for x equals 0, so for x equals 0, x minus 1 is less than 0, but x squared minus 4 is not greater than 0. So this is not true. If I plug in 3, now x squared minus 4 is equal to 9, which is greater than 0. But minus x plus 1, or, well, x minus 1 is equal to 2, which is not less than 0. So this is false. So we pick 1 point here and 1 point here, and the two equations were not verified. At least one of the two inequalities was not verified. But if we pick a point here, both of them will be. Let's pick, for example, x equal minus 3. Now the first one is still going to be x squared minus 4 equal 9, which is greater than 0, so this is true. And then the second one will be x minus 1, which is equal to minus 4. Which is less than 0, which is also true. So that's one. This is the value that is in the system of that satisfy both equations in the system of inequalities. Okay, there's one more topic that I want to look at, which is the sign of fraction. Again, sometimes some of the equations that we look at are expressed in the form of a fraction. You might not be familiar with the velocity of the seismic waves, but the velocity of the seismic waves is actually a square root of some elastic parameters divided by the density. So let's say that we're interested in the square of the velocities, so we don't have this square root here. Now we want to know when this expression is positive or negative. Well, obviously the velocities are always positive, but this is an example of function that is expressed in the form of a fraction. Let's look at an example. So x divided by 3x minus 6. We want to know when this quantity is greater than 0. Well, what we can do is, so we want to know when the fraction is positive and when it is negative. So in this case, we're going to focus on the positive side, and then in the other intervals, it's going to be negative. Well, we're going to focus on the numerator first. This is x greater than 0. This is simple. And then the denominator, it's 3x minus 6 greater than 0, which means 3x greater than 6, which means x greater than 2. Now, we cannot use the same strategy as before. This is not about, obviously, if both numerator and denominator are positive, the fraction is going to be positive. But think about it. If they're both negative, the fraction between of a negative sign divided by a negative sign is going to be positive. So here the goal is not to look at where all the equations are verified, or all the inequalities are verified, but we want to see where they have the same sign, because if they have the same sign, the product of the two is going to be positive. Now remember then, if you have a times b greater than 0, this is going to be true if a is greater than 0 and b is greater than 0. Let me use a more mathematical notation here. Or this is going to also be true when a is less than 0 and b is less than 0. Because if they're both negative, the product is going to be positive, right? Minus 2 times minus 3 is going to be plus 6. If one of the two is positive and the other one is negative, this is not going to work, because minus 2 times 3 is going to be minus 6, which is negative. Obviously, if both are positive, then it's going to work as well, because this is positive. Okay, this was just a simple example, but with numbers, but this should be clear. So now let's go back to our fraction. So we're still going to use our graphical representation. So the solution of the numerator is x greater than 0. The solution of denominator is, so this is numerator, this is denominator, this is x greater than 2. Now, here the solution, both of them are positive, so the final sign is going to be positive. Here, one is positive and one is negative, so the final sign is going to be negative. And here, both of them are negative, so the final sign is going to be positive. So the solution is for x belonging to R, such that x is less than 0, or x is greater than 2. So let's plug in some numbers to see if it works. If x is equal to minus 1, the numerator is minus 1, the denominator is minus 3 minus 6, which is minus 9. So the entire fraction is 1 divided by 9, which is greater than 0. If x, so we are here, and indeed this expression is positive. We pick a number here, for example 3. This is going to be 3 divided by 9 minus 6, which is 3, so the expression is going to be 1, which is positive. Now we pick a number here in the middle, so x equal 1. This is going to be 1 divided by minus 3, which is minus 1/3, which is negative. So a lot of students, especially in high school, are confused by these two processes. This is a system of inequalities where both inequalities must be verified. So I use the same graphical representation, but in this case I'm selecting all the regions or all the intervals where both equations are verified. Here I'm studying the sign of a fraction, so I want to know where the entire fraction is positive. So I study numerator and denominator separately, and then look at the intervals where their sign is the same, either positive or negative. So I'm going to take this region and this region, because in this region they're both negative, which means that their product or the fraction is going to be positive. I'm going to do one more example where we look at negative when the fraction is negative. 10 minus x divided by 3x plus 1 less than 0. Well, we have to do some math first. So we're going to do a common denominator, 3x. This is 10 minus x plus 3x less than 0. So it's 10 plus 2x divided by 3. Oh, sorry, this was... no, this is correct. Less than 0. Okay, so we do the numerator first. This is 10 plus 2x. Now, we want to study the sign of this fraction. So it really doesn't matter if when we do the numerator and denominator we do negative or positive, as long as we're consistent at the end. So I typically always study when it is positive because it's easier to look at. Or you can preserve the sign that you have here. It doesn't matter. Let's be consistent with what I generally do. So 10 plus 2x greater than 0. This means 2x greater than minus 10, which means x greater than minus 5. And then the denominator is 3x greater than 0, x greater than 0. Okay, so we're going to use our graphical representation again. The numerator is positive when x is greater than minus 5. And denominator is positive when x is greater than 0. Now, we could have used the less than instead of greater than. The result would have been the same. We would have had x less than minus 5. This expression was negative when x is less than minus 5 and positive when x is greater than minus 5. So it's exactly the same. Now, we're looking at the intervals where, I don't know what happened here. We're looking at intervals where the sign is the same. Sorry, the sign is different because we want to know where this expression here is negative. So above 0, this is going to be positive. Below less than minus 5, it's going to be positive again because these are both negative signs. And here between minus 5 and 0, it's going to be negative. So the solution is x belonging to the set of real numbers such that minus 5 is less than x less than 0. Well, let's try to plug in some numbers just to see if we did it right. So my guess is that if I pick something like minus 10, this is not going to be negative. If I pick something like 2, it's not going to be negative. But if I pick something in between, it's going to be negative. So let's do it on the original equation just for... okay, so I'm going to write the expression here, and then I'm going to move down the screen. Okay, so this is the expression. For x equal minus 10, we have 20 divided by 30 plus 1, which is equal to 50 divided by 30, which is equal to 5 divided by 3. So this is not negative. So this value doesn't verify our inequality. Oh, sorry, I missed a negative sign here. I did it wrong. Let's redo. Sorry about that. This is 10 minus 10, which means 20, divided by minus 30 plus 1, which is minus 30 20 minus 30 is minus 10, which is equal to 1/3. They're both negative. It doesn't verify the equation. Now I pick x equal to, this is 10 minus 2 is 8, divided by 6 plus 1. This is 4 divided by 3. So this is 7 divided by 3, which is obviously positive. So both of these values are positive when I plug in these numbers. So they don't verify the equation because we're interested in seeing when it is negative. Now I plug in x equal, let's do minus 1. So this is going to be 10 minus 1, it's 11, divided by minus 3 plus 1. This is going to be minus 3, it's 11 minus 3, which is minus 8 divided by 3, which is obviously negative. So this works. Okay, just to recap, what we did is we reviewed how to solve quadratic equations in the form ax squared plus bx plus c greater than or equal to 0, for example. So we solved the associated inequality. And then we just studied the associated parabola and see where the parabola is greater than or equal to 0, which means where it is above or below the x-axis. Then we look at system of inequalities. We can write it like that if you want. And alpha x squared plus, so these are just two different equations, the inequalities of degree 2. So here we look at intervals where both inequalities are verified or satisfied. And finally, we look at fractions of inequalities. I'm going to use a different notation just to make it different. So here we look at intervals where the fraction is positive. Which means numerator and denominator have the same sign. Class. Okay, let's recap the definition of exponential. A power n is equal to a times a times a n times. Correct? So now we're gonna introduce the definition of logarithm, we're going to assume that a is positive. Now, x is going to be defined as the log base a of b. So this means that x is that number such as a power x is equal to b. Now, if we assume that a is positive, then b is also going to be positive. For simplicity, we're going to assume that a is not equal to 1. Now, let's look at some examples. So if I have the log base 2 of 8, so this means the number such that a power x, the number x such that a power x is equal 8, well, this number is going to be equal 3. So the log base 2 of 8 is equal 3. The log base 2 of 32, 2 power x equal 32, means x equal 5. So this is going to be 5. The log, another way to write it is express the base as a function of the argument as a function of the base. So the log base 2 of 32 can be written as the log base 2 of 2 power 5. So the result is 5. The log base 3 of 81 is equal the log of 3 of base 3 of 3 power 4, which is equal 4. The log, if I don't write anything, it's going to be base 10 of 100 is the log of 10 power 2, which is equal 2. The log, the base can be a fraction, for example 2 divided by 3 of 8 divided by 27 is the log of 2 base 2 divided by 3 of 2 divided by 3 power 3, so it's going to be equal 3. Now there are some special cases. If I do log base 3 or anything really of 1, well, I need that number x such that 3 power x is equal to 1. Well, the number is going to be 0 no matter what the base is. So this is going to be 0, and the log power, say 1/5 of 1 is also going to be 0. We can try to come up with fancy examples. The log base 8 of 2. Now, in this case, the argument is smaller than the base, but this is still a power of the base, because we can write this one here as the log power 8, base 8 of 8 cubic root of 8, which is the log base 8 of 8 power 1 divided by 3, so this is 1 divided by 3. Log base 9 of 1 divided by 3, well, this is the log base 9 of 1 divided square root of 9, which is the log base 9 of 9 power minus 1 divided by 2. Which is minus 1 divided by 2. Indeed, if you compute 9 power minus 1 divided by 2, you get 1 divided by 9 power 1 divided by 2, which is 1 divided by the square root of 9, which is 1 divided by 3, which is exactly the argument. So the calculation of exponents and logarithm is based on this relationship here. x is the log base a of b, which means that a power x is equal to b. Now, if a is positive and it's if a is positive, b is also positive too. Let's review the properties of the exponentials and the logarithms. So we said that for the exponentials, a power m times a power n is equal to a power m plus n. A power m divided by a power n is equal a power m minus n. And a power m, then everything power n, is equal to a power m times n. Now for the logarithm, using the relationship above, we can obtain a similar set of rules. The log of a plus the log of b, and this is true no matter what the base is equal to the log of a times b. The log of a minus the log of b is equal to log of a divided by b. And then c times the power, the log of a is equal to the log of a power c. So these are the set of rules that we are going to use. Now, I would like to show you a couple of examples where we work with logarithmic equations and exponential equations. Now for today, probably we're going to look just at the logarithmic equations, and next class we're going to look at some exponential equations. Say that we have this exercise, 2 times the log of x minus 2 plus the log of x plus 5, or that's equal the log of x plus 5 plus the log of x. Okay? Our goal should be to get one logarithmic expression on the left and one logarithmic expression on the right. Say that if we get to the point where the log of a of x is equal to the log of b of x, and the base is the same, then a of x is equal to b of x. So if we can get to this expression here, log of a of x equal log of b of x, then we can say that the arguments are the same. Now here we have to be sure that these expressions are valid. We know that in a logarithm, the base has to be, the argument has to be positive, so we need that a of x is greater than 0 and b of x is greater than 0. So first we have to find the values of x such that the arguments are positive, and then we can say that the first argument is going to be equal to the second argument. Now, most of the times we don't get this expression log of a equal log of b. At the beginning, we have to work with some basic algebra rules to get to that expression here. Now here we're going to use the three rules that we saw before. So on the left side, we can say that this is the log of x minus 2 power 2 equal to the log of x times x plus 5. Now, in this case, we have this expression here is going to be a of x, and this expression here is going to be b of x. Okay? So this means that the log of x minus 2 squared is equal to the log of x squared plus 5x. We need the arguments of the logs to be positive. So um, so the first step is that the arguments of these logs have to be positive. So we're going to have that x minus 2 has to be greater than 0, x plus 5 has to be greater than 0, and x has to be greater than 0, which means that x is greater than 2, x is greater than minus 5, and x is greater than 0. Well, this is a system of equations. So all these expressions of inequalities, so all these expressions, they have to be verified at the same time. 2 is the bigger number, so x greater than 2 is going to be the solution. If you want a graphical interpretation, this is going to be 2, this is going to be minus 5, and this is going to be 0. So it's not really on scale, but so the first expression is going to be positive when x is greater than 2 and negative otherwise, or it's going to be verified when x is greater than 2 and not verified otherwise. The second expression is going to be verified when x is greater than minus 5, and the third expression when x is greater than 0. So all these expressions are going to be verified when x is greater than 2. So the domain of this logarithmic equation is all the x's belonging to the set of real numbers such that x is greater than 2. Now, once we clarify the domain of the expression, we can actually solve the expression. So we're going to use the rules that we have studied. In the first case, we can use the third rule that c times log of a is equal to log of a power c. So this is going to be log of x minus 2 power 2, which is equal to, on the right hand side, we're going to use this first rule that the sum of the logs is equal to the log of the product. So this is x times x plus the log of x times x plus 5. Now we can write this on here as the log of x minus 2 square equal to the log of x square plus 5x. Now at this point, we got to the expression where we have a log of a function of x on the left side and the log of a function of x on the right side. We're going to call the first one a of x and the second one b of x. So what we can do is say, well, then a of x has to be equal to b of x. So we can say x minus 2 square is equal to x square plus 5 square. And now this is just a quadratic equation that we can solve pretty easily. This is going to be x squared plus 4 minus 4x equal to x squared plus 5x. X squared and x squared go away. So now we're left with 4 minus 9x equals 0, which is 9x equal 4, which means that x is equal 4 divided by 9. Now, 4 divided by 9 is the solution of the quadratic equation that we obtain after we switch from the logarithmic equation to the quadratic equation. However, we have to remember what the domain of the equation was, of the original equation was, and it was d equal all the x's in the set of real numbers such that x is greater than 2. Now, 4 divided by 9 is less than 2, so this equation here has no solution because the one that we found is actually cannot be assigned to the logarithmic expression because 4 divided by 9 would make the first logarithm, this one here, less than 0, therefore it's not acceptable. Plus x plus 1 plus 3 equal to log base 2 of 8 minus x squared. Okay, again, the first thing to do is to study the domain of the logarithmic equations. So we need x equation. So we need x squared plus x plus 1 greater than 0. And we need 8 minus x squared greater than 0. Okay, let's study the first one. Every time we have a quadratic inequality, what we do is to study the associated equalities. So it's going to be x squared plus x plus 1 equal to 0. Now we're going to use the quadratic formula. So this is the two solutions 1 and 2 are going to be minus 1 plus or minus the square root of 1 minus 4 divided by 2. Now in this case the delta, so this expression here under the square root, is less than 0. Therefore there are no intersections. This is a parabola that looks upward without any intersections. So this is going to look like this approximately. So this is always positive. So the solution of the first expression is going to be, of the first inequality, is going to be for all the x in the set of real numbers. Now for the second expression, 8 minus x squared greater than 0, we again study the associated quadratic equation. The two solutions, well, this is straightforward. This is going to be x squared equal 8, which means that x, 1, 2, the two solutions are going to be plus or minus the square root of 8, which is 2 times the square root of 2. Now, these are the two intersections. We need to study where the parabola is positive. This is going to be a parabola that looks downward because the sign of the x squared is negative. So, and we know that the intersections are in minus 2 square root of 2 and plus 2 square root of 2. So this is the first intersection, this is the second intersection, and the parabola looks downward because the sign of the x squared is negative. Now, the parabola is going to be positive in this interval here. So between minus 2 square root of 2 and plus 2 square root of 2. So the solution is for all the x in the set of the solution of the second expression of the second inequality, 8 minus x squared greater than 0, is for all the x in the set of real numbers such that minus 2 square root of 2 is less than x less than 2 square root of 2. So we intersect the two domains and we get that the domain of the logarithmic equation is for all the x in the set of real numbers such that minus 2 square root of 2 is less than x less than 2 square root of 2. Now, once that we clarify the domain, we are going to work on this expression here at the top to transform this expression into a logarithm, the equality of two logarithms. Now we have to work on this plus 3 first, but this is a log base 2, so we want to express this plus 3 in a log base 2 of something. Well, 2 power 3 is 8, so we can write this expression here as the log base 2 of x squared plus x plus 1 plus the log base 2 of 8 is equal to the log base 2 of 8 minus x squared. Now we can apply the rules of the sum of the logs. So this is the log base 2 of 8 times x squared plus 8 plus 1 equal to the log of 8 minus x squared. And now this is the log of a of x, this is the log of b of x, so we can just say 8 times x squared plus x plus 1 is equal to 8 minus x squared, which means that 8x squared plus 8x plus 8 is equal to 8 minus x squared. Now 8 and 8, they go away. So what is left is 9x squared plus 8x equal to 0. Now this one here has two solutions. We factor out x, and this is 9x minus 8 plus 8 equal to 0. So solution number 1 is x equal to 0. Solution number 2 is it would be 9x equal to 8, which means that x is equal to minus 8 divided by 9. Now, both these solutions, both x1 and x2, are less than 2 square root of 2, because 1 is 0 and 1 is negative. Now this one here is greater than minus 1. Minus 2 square root of 2 is less than minus 1, so they're both in the domain. So both solutions are acceptable, and these two solutions are actually the solutions of, these two numbers are actually the solutions of the logarithmic equation. Let's look at a couple of other examples, just so that just so you get familiar with these. The log base 2 of x minus the log base 2 of x plus 4 plus 1 is equal to 0. Now again, we studied the domain. This is pretty simple. X greater than 0 and x plus 4 greater than 0. So it's x greater than 0, x greater than minus 4. So the domain is x greater than 0, or all the x's in the set of real numbers such that x is greater than 0. Okay, now we have to work with the logarithms. First of all, we want to transform this plus 1 in the log of 2, so this is going to be log of 2x. We can move the logarithm with the negative sign to the right, so this is going to be the log base 2 of x. 1 can be written as the log base 2 of 2, and then we move this one here to the right, so this is going to be the log base 2 of x plus 4. And now this is simply the log base 2 of 2x is equal to the log base 2 of x plus 4. Now we can just say that 2x is equal to x plus 4, which means that x is equal to 4. Now 4 is positive, so this is the solution of the logarithmic equation. Would like to do a couple of other examples. Log of x minus 16 is equal to the log of 105 minus the log of x. Again, we know how to do it. We studied domain x minus 16 greater than 0, and x must be greater than 0. 105 is obviously greater than 0. So this is x greater than 16 and x greater than 0. 16 is greater than 0, so the domain is for all the x in the set of real numbers such that x is greater than 16. Now at this point, we can work on the logarithmic expression. This is the log of x minus 16 equal to the log of, this is going to be 105 divided by x, since there's a negative sign here. And so x minus 16 is equal to 105 divided by x. Well, we know that x is positive, so we can multiply, because by definition it has to be greater than 16, so we can multiply both sides by x. So this is going to be x squared minus 16x equal 105. So this is x squared minus 16x minus 105 equals 0. And now we can study the two solutions. x12 is equal to, we can work on b squared instead of on b divided by 2. So this would be 8 plus or minus the square root of 64 plus 105, which is 8 plus or minus the square root of 169, which is the square of 13. So it's 8 plus or minus 13, which is equal to, well, 8 plus 13 is 21, which is okay. And then 8 minus 13 is minus 5, which is not okay, because it's not greater than 16. Indeed, if you try to plug in minus 5 in the first logarithm, or even in the second one, well, these two expressions are not defined for x equal minus 5. X equal minus 5. Okay, let's do one more. The log base 4 of x plus 6 plus the log base 4 of x is equal to, now we start domain x plus 6 greater than 0 and x greater than 0. This is x greater than minus 6, x greater than 0. So the domain is all the x such that x is greater than 0. Then now we can write these two as the log base 4 of 16. So this is the log base 4 of x plus 6 plus the log base 4 of x equal to log base 4 of 16. We're going to use the rule of the sum. So this is the log base 4 of x times x plus 6 equal to log base 4 of 16. This is x squared plus 6x equal 16. So this is x squared plus 6x minus 16 equal to 0. And now we just have to solve the quadratic equation. x1, 2 is going to be minus 3 plus or minus the square root of 9 plus 16, which is the square root of 25, which is 5. So it's minus 3 plus or minus 5, which is minus 8, which is not acceptable, and plus 2, which is acceptable. Okay, so we saw 4 or 5 examples, 6 examples, where we solved equations involving logarithm. At the beginning of next class, we're going to look at some examples where we solve equations with exponentials. And then we're going to switch to derivation and integration, and then the recap is going to be over.